Have you ever imagined what it's like inside a distant alien atmosphere? How the clouds form, what chemicals swirl around, or how the temperature changes from top to bottom? In this video, we'll explore what some are calling the first 3D observations of an exoplanet's atmosphere, an incredible discovery that reveals a very unusual climate on a planet called GJ504b. By the end of this video, you'll learn how astronomers pieced together different layers of data, almost like building a 3D map, and used it to confirm the presence of ammonia in a surprisingly cool atmosphere. Let's jump right into it. There are nearly 5,000 confirmed exoplanets outside our solar system. Most of these have been discovered through indirect measurements, like how their host star's light dips if a planet passes in front, or wobbles if a planet tugs on it. These methods don't usually tell us anything about the planet's weather. And yes, exoplanets can have weather, just like Jupiter's famous Great Red Spot or Saturn's swirling cloud bands. But how do you figure out the weather on a planet so far away you can't even see it with the naked eye? That's where the James Webb Space Telescope comes into play. Its advanced detectors let astronomers observe these distant worlds in the infrared spectrum, a type of light we can't see but which carries vital clues about temperature, altitude, and what the atmosphere is made of. What's special about GJ504b is that it's relatively close to Earth on a cosmic scale. It orbits a star bright enough for JWST to lock onto, but faint enough that we can tease out the planet's own glow. Astronomers suspect GJ504b is either a high-mass planet or a low-mass brown dwarf, sitting right at that borderline. Studying its weather provides an unprecedented glimpse into these in-between objects. And that's where the 3D approach comes in. Calling it 3D might seem like a buzzword, but the idea is simple. You don't just look at one layer of a planet's atmosphere. Instead, you gather data at multiple infrared wavelengths, each of which probes different altitudes or depths within the clouds and gas. Near-infrared light tends to see hotter, shallower layers, whereas mid-infrared can reach cooler, deeper layers. By combining these data sets, astronomers piece together a more complete vertical profile of the planet's atmosphere, like stacking slices of a cake to see it from top to bottom. In the past, telescopes like the Very Large Telescope, Subaru, and other instruments used near-infrared cameras to barely spot GJ504b. These observations showed that GJ504b is relatively cool compared to scorching hot Jupiter-like exoplanets. However, the data were not detailed enough to confirm certain molecules. This is where the James Webb Space Telescope truly shines. Its mid-infrared instrument MIRI zeroes in on longer wavelengths, allowing us to look deeper. Each MIRI filter picks out a specific slice of the spectrum, so if there's a particular gas that absorbs or emits at that wavelength, it stands out. By stacking the near-IR and mid-IR data, astronomers achieve a more layered picture, hence a rudimentary 3D understanding. GJ504 star is bright, so the planet is normally invisible. The MIRI coronagraph works like putting your hand in front of a flashlight so you can see faint things near it. JWST does exactly that, but on a grand cosmic scale. Even then, there's still star spillover, which astronomers must remove through sophisticated image processing. Combining these steps effectively yields different layers of GJ504b's atmosphere. As each filter sees a different depth, the net result is closer to a true three-dimensional profile than a single image could ever be. Once the starlight was subtracted and GJ504b's own glow stood out, astronomers began checking how bright the planet is at various infrared wavelengths. When they matched these brightness levels against theoretical models of planetary atmospheres, one thing became clear. GJ504b's best fit model requires ammonia. But why is ammonia such a big deal? Here's a quick rundown. Ammonia generally forms or remains stable in cooler environments. Detecting it implies that GJ504b has a relatively low temperature for a gas giant, hovering around 500 Kelvin, roughly 230 Celsius. The presence of NH3 suggests an atmosphere rich in nitrogen chemistry, possibly with other molecules like methane or water vapor. Each molecule provides hints about how this object formed and how gases are circulating at different layers. In cooler, ammonia-bearing atmospheres, you can get layers of cloud decks that might include water clouds, ammonia clouds, or sulfide clouds. This layered cloud structure likely influences the planet's visible appearance and potentially leads to dynamic, swirling weather patterns. All these factors point to what researchers call a unique climate. Unlike the scorching, clear-skied environments found on many exoplanets, GJ504b's layers of ammonia-influenced clouds and moderate temperature set it apart. It seems we've uncovered a world that's partway between a massive Jupiter-like planet and a brown dwarf, with an unexpectedly rich atmospheric story to tell. Finally, let's talk about the bigger picture. Why these 3D observations and the unique climate matter in the grand scheme of exoplanet science? Every time we learn details about an exoplanet's atmosphere, we refine or revise our theories of how planets and brown dwarfs come into being. If GJ504b is truly cooler and holds more nitrogen-rich chemistry, it might have formed farther from its star in a colder, denser region of the protoplanetary disk. Alternatively, it might have formed more like a star, collapsing from a cloud of gas. That distinction is crucial for understanding the dividing line between planet and brown dwarf. GJ504b also allows us to demonstrate that JWST's MIRI instrument can accomplish what was practically impossible before: mid-infrared observations sensitive enough to detect molecules like ammonia around a faint object. This test case gives astronomers confidence to apply the same methods to other planetary systems, hunting for water vapor, carbon dioxide, or even more exotic molecules. Although GJ504b is not a candidate for life as we know it, it's still a giant world. Proving that JWST can pick up molecular fingerprints in cooler atmospheres is a game changer. It hints we can explore even smaller, potentially habitable planets in the future, measuring water vapor or other biosignatures on rocky worlds. Above all, each new exoplanet we investigate shows us how varied and surprising the universe can be. From boiling hot Jupiters with molten metal clouds to these cooler, ammonia-laden worlds, we see that nature creates an incredible range of climates. By extension, the environment on Earth, with our nitrogen-oxygen atmosphere, is just one stop in a very wide spectrum. That's the big reason these findings matter. GJ504b expands our picture of possible planetary environments and proves we can measure them in detail. Who knows? What other atmospheric secrets might be revealed by further JWST observations?